Hello, my name is Stachniss and I would like to welcome you here to my talk on vehicle localization, and I want to especially thank the organizers of this event to invite me to speak here. I want to talk about how we can use non-metric information to support vehicle localization. So in the end, we of course want to localize our vehicle in the metric space, but the question is, how can this non-metric information actually help us in our localization system? And the work that I'm presenting here is work that is done by several people from my lab, so a lot of the credits of what I'm actually presenting here is their work. And I want to start with arguing for using this non-metric information by saying that vehicles must operate under very varying conditions, and the world around us changes, and so its appearance. So we want to have autonomous cars or other mobile vehicles that navigate through the space and can estimate where they are. And for that, they need to deal with challenging situations. So what you see here are pairs of images, those pairs and those pairs, which have been taken at the same location but at a different point in time. And what you can see is that the appearance of the space has substantially changed. The question is, can we deal with such strong appearance changes and still build a system that can localize or make the data association recognize the same place and saying, yes, this vehicle is at a place where it has been before. And that's what this, or the first part of this talk, is about. And just to show you that this is based on individual images, a challenging problem, I brought you a few pairs of images. And so let's see if you are actually able to identify if this is the same place, yes or no. So question, is this the same place, yes or no? I think that one is easy. It's a yes. We can see this building is quite distinct. Hold this flag. One image has been taken in summer, the other one in winter, but we as humans are still able to identify that. Let's go to the next example, this one over here. First would say, yeah, that actually looks pretty much the same, but it turns out no, it is not the same place. It's not even the same street, it's a different street, but in the same neighborhood. And you can see it, for example, there's a tree over here, this tree is missing, but maybe they took down the tree, you never know, but it is definitely not the same place. And then I have the next example over here. Is this the same place? Yes or no? Again, it's a similar neighborhood. In Freiburg, if you drive around, you experience those images, but it turns out it's not it is the same place, although it doesn't look the same. And you can see it here. This building over here has been demolished, so the building doesn't exist anymore. The space appears different and looks different, but it's actually the same place. So it turns out that doing this recognition task based on individual images is quite challenging, but we can actually do that if we take sequences of images into account. So if we take into account that we have been recording one image after the other and we exploit this sequential information to align image sequences, this becomes a much easier problem. So they can use it in a localization system by exploiting this temporal or sequential information. And what I can do is, let's say I have one database recorded or one image sequences which I use as my database, maybe associate even with map information during a mapping task, which I recorded, let's say, in winter. And now I'm driving around in summer and I want to take just the image information and match them against the previously taken image. How do I do this? Let's say start with the most naive case. We build up a matrix where we compare every image of our query sequence with every image of our reference sequence. We compare those images, for example, based on feature descriptors that we compute from those images, or any other way for comparing those images. And then we end up getting such a cost matrix over here. So bright values mean images look similar, dark values, images appear differently. And you can see just based on individual dark and bright values, it's actually hard to say where the vehicle has been. If you take the full matrix into account, so exploiting the sequence, you can see that here is a bright line going through this matrix. And this is actually the trajectory that the image has been taken. And by using this kind of full matrix, we can actually try to find a kind of path through this matrix. In this way, find the best matching pairs of images. So technically, we can build up a so-called data association graph. So a graph in which each node represents a data association, a match between two images. And then we can plan a path, the shortest path through this graph, which will give us the sequence of matched images. And the cost of this path, the cost of a node, is basically the cost a cost which is computed based on the similarity of those images. And through this path through that graph, and by taking a local connectivity into account in this graph, we can actually exploit this sequential information. So that by planning a path, we'll find a path through these nodes, through this graph here shown as the red nodes, and in this case a blue node is a so-called hidden node. There's a node along the path, so we know the system has been there, although the images look not very similar. And this is something we call a hidden node, so something where we couldn't find a match based on an image, but based on the sequential information, we know the system must be here. And given this, we can align those image sequences and can align one trajectory with another trajectory, although those images have been taken under very, very different conditions. The problem that we have with this approach is that we need to compute this full cost matrix. And this is computationally expensive because we need to compare every image of my query sequence with every image in my database. And this is something which we can't do in real-world situations. So the goal is to bring this towards an online approach where we don't need to expand the full graph, but only part of the graph. The part which is shown or illustrated in green here. So if we only need to compute those green paths in there, let's say the most promising images, and then find a path in this, through this kind of promising region, then we may be able to do this in an online fashion. And we can actually do this, we can build up this graph on the fly so that we don't need to compute the full cost matrix, but only the cost matrix here shown in green and everything here in black actually doesn't need to be computed. So we want to avoid computing this part and only compute the green region so that we then can find an efficient path. And the question is, how can we actually realize this? How can we do this? And the goal, or how we can achieve this, is by simultaneously building up the graph during the search. So we don't build up the full graph first, we only expand those neighboring nodes that we actually need to compute. And in order to do this in an efficient manner, we need to have a good heuristic. So we know this from graph search. Informed search techniques such as A* are very efficient if we have a good heuristic. And a heuristic is a technique to provide a lower bound for the cost that will be generated if I go from a current node to my goal node, and I need to provide a lower bound estimate for that. And then I can basically turn into a lazy data association, traversal or building up of the graph, and expand only those nodes which currently look the most promising ones, and in this way expand only a small fraction of the graph, but still are able to find my matching sequence through that graph. If you think about informed search, you probably think about A*, but it turns out A* doesn't really work well. And the reason for this is that it's very difficult to design a useful and admissible heuristic. Admissible means you need to underestimate the cost and have a zero cost at the goal. And useful means that it's actually not just a zero function, it provides useful information. And this is different to a search in the Euclidean space, for example, where the straight line distance gives me a good admissible heuristic. Here we are in the space of image similarities, and here it is much, much harder to come up with a good heuristic. So what you need to do in this graph search, so you are in a certain node, let's say you expand it up to this node, and now another node looks more promising, like this one over here. Then in our data station graph, we need to estimate how expensive is it to go from here down to here and match the next L minus I images. And we have done this using a heuristic, which is not an admissible heuristic, so it's not guaranteed to provide a lower bound, but which takes into account the average cost of the best path found so far, multiplies it with a factor which is smaller than 1. So we say, let's say, we expect the best path to be only, let's say, 80% of the cost of the currently best found path. This is an assumption that we do in here. And then multiplied with the number of images. So we have our expected cost for an image comparison along a matching sequence. We have the images we need to match and this expansion rate, or this factor which scales the cost down in order to allow us to search, explore other alternatives. The problem with this heuristic is that it changes during the search because we find better paths, so we get better estimates of the expected cost, and this prevents us from the use of A*. So we have to modify our search algorithm a little bit to take into account that our heuristic may change during the search. But if we do this, we can actually perform this online visual localization of place recognition in changing environments. And you can see here our images. So this is our database images. You can see where this image has been taken and the current estimate of where we are. You can see here the vehicle is driving to a path that hasn't been mapped before, which is this road over here, so it doesn't find any match. But as soon as it re-enters known parts of the environment, it can establish the data association and can actually localize these images. And localize means here, through the matching with the database, we know where we are, and in this way can localize the vehicle just based on this image. Again, this is something which you wouldn't, of course, not use for a standalone localization system, but you may integrate this into an existing metric localization system to tell you where you are on a global scale or provide you with an alternative means to estimate your position on a global scale. And so this online search actually helps a lot to reduce the number of computations. So you can see here a rather large cost matrix from the V-Price challenge for performing this place recognition in those environments. And you can see here only a very, very small area in this graph actually needs to be explored. In this case, had only been 0.5% of the overall comparisons that need to be done. If you go to other very challenging environments, the number may be a bit lower, but you still only need to explore a fraction of the graph. So that you can actually run this on a real platform and multiple times per second perform those comparisons. You can again see here the current image, the corresponding database image, and here the part of the cost matrix that is actually computed and explored during the search. So this is kind of a zoomed in view of the expanded cost matrix, and you can see here how the system only needs to explore a small part of this matrix and actually finds the data association here. We can also do this, for example, over a day-night drive. So again, here we are driving at night and localize with respect to an image sequence that we have been recorded during the day. And even here, under this strongly changing conditions, we only need to expand a small part of the search tree. And we can also show that we can find multiple hypotheses, can track multiple hypotheses over extended periods of time if we, for example, have two trajectories which look very similar. So that's actually an interesting thing, that just by this exploiting this sequential information, we can quite robustly estimate image sequences, although the appearance of the environment has changed substantially. And again, as a short reminder, we have done this using purely visual information. No geometry has been used, no connectivity information except the sequential information, no odometry, no visual odometry. No cameras need to be synchronized. Really, the cameras are just exposed, let's say 2 or 3 times per second. We have this image and just use these image sequences. And we can perform this localization just with this image information. This was, however, only part of the truth. So there are situations where the system can fail and may fail. And one of the reasons is if we have very flexible trajectory, drive on flexible trajectories. For example, if we deviate from our originally taken trajectory and drive to a part of the environment where the system has never been. So then the system basically gets lost, re-enters the space at a later point in time. The question is, can we follow up on that? Or if we have taken shortcuts on our current route with respect to the reference trajectory. It's also something which currently cannot be handled. You can see it here in those cost matrices where this was a path and I'm going, and then the system would actually need to jump over here and continue the search here. Or we have areas in my matching matrix where we can't find any match. These are those 2 areas over here where the system has been somewhere else. So if I, for example, run this in this first setup where there's no match here, this is a matching trajectory, and this is a matching trajectory. We will find the first one, or may find the first one. Well, finding the second one is just by chance. It's just luck, because we have been somewhere else, which in an area which is not part of the map. This, however, is a problem which is not novel. This is something that has been investigated in the past. And one prominent example here is the kidnapped robot problem in Monte Carlo localization. So this is a AAAI paper from 2000. And what the authors here suggest is that if the sensor data doesn't fit to my current state estimate anymore, in this case a particle filter, a good idea is to sample new particle locations based on the observation model. So take the observation into account to sample new hypotheses to see if those locations do a better job. And so what we need to do in here is, if we kind of don't find good matches anymore, we need to find other places that are potentially good matches. The only question is, how do we actually find them? So how to find potential matches in this large database. So what we have done in order to do this is a technique inspired by locally sensitive hashing, where we use a hashing technique in order to find other potential matches. It's kind of a form of an inverted index, taking into account the different dimensions of the feature, binarizes those features, and then basically looks into the zeros and ones in the individual binarized dimensions, and then tries to find with an inverted index potential images that look similar to the current image. And it turns out that this is a very good technique to find potential re-entry points for my search. It's not that this hashing technique always provides me the best image or matching image. So what we do is we look for a certain number of potential matches, use those matches to expand, to create new neighbors in this data association tree search, and then through this similarity we have potential comparisons, compare those images, and if we find a good matching one, we can continue with this hypothesis. So again, we had this example. In this part of the environment, we have deviated from the trajectory, the system was lost, and the standard approach really failed, so it only found this part of the trajectory, and then just by chance the last one, but this was just actually good luck. But everything else doesn't really work well. And if we use this hashing technique, so whenever we can't find a good match, we use this hashing technique and see if we can find re-entry points somewhere else. And it turns out that the system is able, with this hashing technique, to say, I don't find anything up here, then finds the correct re-entry point here, localizes the system appropriately, then it gets lost again, it starts sampling, see there's these blue dots over here, probing locations, but they're not very promising, so it doesn't expand them further until it gets an image which is similar to a place it has been already. And then at some point in time, the hashing technique actually finds the re-entry point, expand the search, and I'm actually able to localize my system. So with this hashing technique, I'm actually able, in a lot of very situations, actually find those re-entry points, relocalize the system by just creating a few new neighboring edges in this data association tree. And I can use this also to, for example, localize along multiple trajectories. So if you have multiple reference trajectories, not only one, you can use this hashing technique to simply find re-entry points in multiple of those trajectories. And I just brought you a few examples how that actually looks like. So this is a trajectory, with a query trajectory taken with a car, and there are several, I think in this case 3 or 4, trajectories had been taken before, recorded, and then the system localizes the trajectory that I'm currently driving with respect to the query trajectories. And you can see here the correct matches in terms of in green, and wrong ones, which are false positives or false negatives, where the system missed an image, but through the sequential information, of course, can recover its position and knows where it actually is. So that if I then compare where I was driving with the trajectory I've been matching to, we can see that, of course, we only need to find one color. As long as we found the correct color, everything was done well. So here I was localizing on the red trajectory, then I switched to black, and then here to the cyan trajectory, because this was the most similarly appearing place in this scene. We can go a step further and actually use street view images and localize a dashboard camera using street view images. So in this example, we just recorded a data set in Kiev, driving through Kiev, and matched only against street view images. By extracting image sequences, virtual drive through street view, I'm actually able to localize my camera in my car in this environment. And that's actually very nice, because this is much closer to a map, because I can just use existing image material just from street view in order to localize myself, my vehicle, in this environment. And you can also see the trajectories that we recorded, and then matching this against the generated sequences out of Street View, so they can actually localize in the Street View data. I can even take this a step further and start taking a random YouTube video, and so nothing we have recorded on our own, something we just found on YouTube, and localize it against Street View images. So we can take videos we found randomly on the web from dashboard cameras, which a lot of people upload, and actually localize those images. Again, I don't have ground truth information over here, and doesn't work as well as with the trajectory that we had recorded, but you can see that you can localize a large number of frames that you found in this YouTube video actually within this within the Street View images, which is actually a very nice indicator that this is a robust system for localizing these sequences of image material. So as a short kind of summary so far, what we have done, we proposed a system for visual sequence-based place recognition that exploits the sequential nature of the data and works in changing environments. So in different seasons, matching current images against Street View data. So even if the environment has changed substantially, we can do this in an efficient way. And we can do this in online fashion, build up this graph on the fly, dealing with multiple trajectories, and also the hashing approach really helps us whenever the system is lost or is deviated from that trajectory. And the next question is kind of now, most of those cars actually have laser range data on board as well. So can we use laser range data to do something similar, to localize with this data? And it turns out, yes, we can. So this approach is slightly different. So we could use this data association graph idea as well for the approach here, although we haven't really done that because this work started as a technique for improving loop closing in SLAM. So whenever you build a map of the environment and localize yourself in the map, which is called often simultaneous localization and mapping, then you want to find those re-entry points, those loop closing points, and you can use a place recognition system for that. So this is an example. We have two 3D scans of a car. One, the car is driving around here. The other one, the situation is driving down here. And the question is this the same place? And we can rephrase this question as, do actually the 3D scans overlap? And if those 3D scans overlap, I should be actually able to find a loop closure over here. And I want to focus on this question: do these 3D scans overlap here? And scan overlap, or is something that is an older technique from photogrammetry, where you look into images or image overlap, and we just use this on range images that are taken from a 3D lidar, such as a Velodyne or an Oyster scanner. So we have a scan A and a scan B, and if we kind of put the scan to the same location, we typically generate a higher overlap between the scans, or get a higher overlap, rather than situations where they are not aligned. And again, this overlap has no idea where those images have been taken, but you want to estimate what's the overlap between this scan. And what we have done here is actually using a neural network-based approach, which is fed with training data of images taken at similar locations and from other locations where scans overlaps and don't overlap, and tries to estimate this overlap. And that's a technique that we've presented at RSS this year, and it was a technique for finding loop closures. Again, not using any metric information for finding these loop closures. And how the system works, just kind of in 20 seconds, we have different information, such as the range information we have from our scanner, normal information, intensity information, and also semantic information that are estimated from a semantic segmentation system from those two scans that we have been taken. And then there is a Siamese network with the two legs over here, and then there are two hats. One estimates the overlap between the scan, and the other one estimates the yaw angle, so the rotation around your yaw. And then gives me an estimate on how similar those scans are. Again, there's some pre-processing involved in terms of computing normals from the intensity image, taking this information into account. Then we have our network structure, the overlap network with the two legs and the two heads, which then provides me with the output information. So what I get is an estimate of the overlap, so how much do the scans overlap, and what's the yaw angle rotation among them, and so that I can use this information then for finding loop closures in the context of SLAM. And that's something that we have done, integrated this into Zuma, one of the LiDAR-based mapping systems that have been developed by Jens Belay from my lab. And what we can see here, so the blue thing is a standard loop closing technique so far used in Zuma, and the green curve is the approach with this overlap network, not using any geometric information, and the red one is this overlap network if we take the pose uncertainty that we have in our SLAM system into account as well in order to find those closures. And so this overlap net can be used for lobe closures, so for doing place recognition based on 3D LiDAR scans, without using metric information tells where we are right now, but of course there's metric information in the local scan. And what overlap net does, it predicts the loop closures also in very challenging situations where you have very little overlapping areas where current loop closing systems typically fail, and is now part of our Zuma system. And the question that we have after we have developed this work for RSS here is kind of, can we use this idea of overlap for localization as well? Because it is very similar to a place recognition system, so how can we actually integrate this, or can we integrate this into a localization system? And we started here out with good old Monte Carlo localization, so a particle filter-based localization system, which basically has two steps. It takes a sampling from a motion model, so where's the system at the current point in time, given we know where it's been before, and some odometry command, and then the correction step of this recursive base filter is done with the observation model, so the likelihood of the observation given the pose and the map. And for computing this observation model, we now want to take the overlap net into account. So we use this idea of overlap, so we put in our query scan, the scan that we currently have, and a map scan, so a scan that has been taken at the location when we were building the map, and then compute this overlap. What we can also do is, what we do in practice, we build actually a 3D model of the environment in the mapping phase, and then generate virtual frames at different locations in the environment, just on a small grid. So that's those map scans, actually pre-computed scans, taken at different locations based on back projection. So we need to compare them, and this is an operation which is done on a per particle basis, or for particles that are very nearby, we can actually group this operation so that we are then able to compute an observation likelihood for that particle using this idea of overlap. And so we generate those, in this example, a map for all those blue locations here, this kind of virtual scans. So we kind of zoom in, there's the area have been taken, we put a grid on this, and then can, as an example, take 3 locations over here. In practice is a 20 centimeter grid, and then compute virtual scans, store them in the map, and use them then for the comparison. So we have kind of those map scans, and then we need to compare the query scan to the map scan of the individual particle. So every particle will generate one of those map scans and be compared to our actual scan. And then we can use this overlap net architecture to actually come up with an observation model that we then can use in Monte Carlo localization. And again, these are kind of rather fresh results. We can then use this in order to estimate a vehicle. So we do a localization. You can see the particle filter over here, converges successfully after a small amount of time. And then we take the current 3D scan that we have, take the generated map scan, and then can perform a particle filter-based localization system and track the system over time. And again, just using this information that is obtained kind of in a kind of topological way. And this is again done only with this 3D LiDAR scans, not taking other information such as visual information or other things into account over here. However, if we go to real autonomous vehicles, then we typically have maps that may look like this. So this is an example from a map used by one of my collaboration partners. 2 of my PhD students that I mentioned in the beginning work for Volkswagen and work on localization there. So this is a map where you have certain features or poles which you can see, lane markings, and you want to localize in this map using your data. And what you typically do, you do kind of a local data association between what you see right now and your environment. And then often to make that robust, there's a map matching step involved. So you take the full map and perform a full match of that map. This, on the one hand side, allows you to recover from failures quite quickly, and this is similar to this kind of more global approach, where you could also use image information to see if you have deviated from the trajectory and the system hasn't realized this. Then temporal smoothing is involved in this case. It's not a particle filter, it's a graph-based or vector graph-based approach in order to perform this estimation. But the steps take the sensor data into account, doing local data associations, but you can fuse this global information in there as well. And how this online optimization can be done in an efficient way was the work done by Christian Meerfels. It's a sliding window optimization approach based, he developed it for postgraph, but you can transfer it in the same way to vector graphs. It's a black box integration system where you can have different post information or post sources you can put in and very seamlessly integrate visual odometry, laser-based localization, place recognition just into that system by fusing this into this post graph. By today, we transformed this into a vector graph representation, and you have those vectors between the nodes you want to estimate, such as landmarks and vehicle positions, or can even be map reference frames. And one of the key things is here you can have GNSS involved, but you can also have these alternative sources in there, such as the localization capabilities of place recognition systems I've explained before, and you can feed them in the same way like you would do with a GNSS node. So that in the end, you can actually realize a localization example. So this is an example by Daniel Wilbers, doing this at Volkswagen, where you use all this information that I've presented. You build up this graph on the fly. You fuse in data for matching poles. You can also integrate visual information and other sources in order to localize your vehicle and do this in an online fashion and estimate within a few milliseconds where your platform is and integrate all those sensoring information in order to localize your vehicle. With this, I come to the end of my talk today. So what I hopefully have shown you is that you can use image data and LiDAR data for place recognition and vehicle localization. So I talked more about the place recognition part, but you can integrate it into the localization system itself. Sequence information helps, especially if the environment changes substantially. I think we've seen this nicely in the first part about image localization, and those topological information helps me to also localize the system metrically and can be quite elegantly integrated through this vector graph optimizations. With this, I come to an end. I would especially thank Olga, Reini, Jens, Christian, and Daniel for their contributions to this work, and also for all the parts I talked in the beginning, except of the last part. Everything is available as open source, so you can download this and try the stuff yourself. So I hope that was entertaining and you enjoyed this talk. Thank you very much for the attention, and I wish you a nice remaining conference. Thank you very much.